So welcome to the first ever run through of a question 2 on an RPA paper. I hope you enjoy this as much as you enjoyed the first one. So what you're going to do this time is to find ways to distinguish between these pairs of compounds. Now it says you've got to use chemical tests. That means no spectroscopy, no things like melting points and stuff like that. It's got to be reactions where you can see a colour change or hear an explosion or whatever it might be. So the first one is very standard thing in A-level, which is distinguishing aldehydes like this with the CHO group at the end from ketones, and the one you probably thought of was Tollens reagent. So you warm with Tollens reagent and the aldehyde gives a silver mirror and the ketone doesn't react. Remember to say that, remember to say what both of them do. Aldehyde gives a silver mirror, ketone doesn't react. The reaction that takes place with the aldehyde is oxidation. Tollens reagent is an oxidizing agent, so you can just write it as plus magic oxygen to represent the oxidizing agent, and that will turn into pentanoic acid. So 1, 2, 3, 4, 5, OH. And it's as simple as that. The other things you might be asked on another occasion is what Tollens reagent is, so you have to remember it's silver nitrate dissolved in aqueous ammonia. Okay, that's it for the first one. The second one, you've got to distinguish phenol from benzoic acid. You've got to be careful here. You have to remember that phenols are acidic, and so obviously is benzoic acid. So you can't use any tests that are based on acidity because they would both do it. Nor can you use metallic sodium, which you might have thought of. Remember, metallic sodium reacts with anything that has an OH group and fizzes and gives hydrogen, so it's a good test for OH groups, but they've both got OH groups, so that's no good either. What you can do is again exploit the reactivity of this ring. Remember, the OH group activates the ring, and as far as A-level is concerned, only OH groups do that, and certainly COOH doesn't. So this will not have an activated ring. So you can use the reaction with bromine in the absence of a catalyst. So if you just add aqueous bromine, no catalyst, this will react and decolorize the bromine. The benzoic acid won't. Okay, so the reaction that takes place is for the phenol, and it reacts with 3 moles of Br2, because remember the OH group activates the ring at the 2, 4 and 6 positions. You need to remember that. 2, 4, 6 are activated. So 3 moles of bromine are needed, and I'm going to run out of board here. Let's rub this off so that you can put the reaction in here. And that gives you OH there, and then bromine and bromine and bromine, plus 3 HBr. Remember, in substitution reactions, you always get these small molecule products as well. So that's the reaction that takes place. It's electrophilic substitution, and it happens because the OH activates the ring and the benzoic acid, the COOH, didn't. Okay, third one, I just have to clean the board for this one. Right, the third one is a mean, nasty, ugly question, as I'm sure you decided when you were having a go at it. It's in there really to prompt you to remember that you need to know stuff from AS. So this is halogenoalkane chemistry, which was there in AS, and the problem is that they feel free to ask you about it at A2. You know, it's perhaps unlikely they'd ask you in this much detail, but who knows? So if you haven't done yet, make sure you look back at things we haven't really done much of this year. Halogenoalkane chemistry, alkene chemistry too. Make sure you know those addition reactions of alkenes. Okay, so what we're doing is distinguishing iodobutane from chlorobutane. So we've got that with iodine and that with chlorine. So what you can do is recognise that they will both react with aqueous sodium hydroxide, or indeed with water, which is the same reaction, just a bit slower. And when they do that, they release halide ions. So if you do the iodobutane, it will react with water to produce butan-1-ol. Okay, so you get a substitution reaction, and HI, but remember that's an aqueous acid, so it's broken up into H plus and I minus. Okay, and likewise this will do the same thing. Again produce butan 1ol plus H plus Cl minus. Now what you do is you do this reaction not just in water but in aqueous silver nitrate, because then as soon as these halide ions are formed, they react with the silver ions and precipitate out the silver halide. So for example with I minus you get this reaction, Ag plus I minus goes to AgI, and this will precipitate out the silver chloride, and that gives you two ways you can possibly use to distinguish them. One is that silver iodide is yellow whereas silver chloride is white, so you could tell which is which, because if you do this reaction in aqueous silver nitrate, iodide ions are released and they form a yellow precipitate with the silver ions. If you do it with the chlorine, chloride ions are released and they form a white precipitate. Or you can rely on the difference in the rate, that the carbon-iodine bond is weaker, remember, than the carbon-chlorine bond, so this one hydrolyzes much faster, so you get the precipitate much quicker with the iodoalkane than you do with the chloroalkane. Okay, so that was just a prompt to remind you to look at halogenoalkane stuff in AS. Okay, that's it for question 2. Back with question 3 shortly.